Lesson 5 Summary. Basic Circuits. A note from your instructor, Jerome Barnes, read by Hector Bello. This lesson contains a lot of formula-based computations, so get out your calculator and be prepared to brush up on your basic math skills. Make sure you understand how to find current, voltage, resistance, and power, because you'll need to be able to conquer these calculations throughout the remainder of the course. In this lesson, we will discuss three types of electrical circuits. In terms of wiring components, the three types of circuits are series, parallel, and combination. Before we delve into the circuits, let me show you a short list of what some important symbols represent. E is voltage, I is current, R is resistance, P is power, ET is voltage total, ER1 is voltage across R1 and can be more than one and will be labeled in sequence ER1, ER2, ER3, etc. IT, current total. IR1 is the current across R1. The same rule will apply if using more than one resistor. RT is resistance total. PT is power total. PR1 is power across R1. The same rule apply if you use more than one resistor. In a series circuit, figure 5.1, there is only one path for the current to flow. In a series circuit, there are certain rules you must adhere to. These rules will help you understand the circuit better. They will also make troubleshooting a lot easier. Refer to figure 5.2 on the next page when reviewing these rules. Voltage is a series circuit. Voltage in a series circuit is additive, Kirchhoff's law. This means you must add all of the voltage drops together to get the total voltage. Looking at figure 5.2, you have to add the voltage drop across each resistor to get the total voltage, or ET. Current in a series circuit is the same throughout the circuit. This means whatever the applied current is, each component will see the same amount. Looking at figure 5.2, you have 5 amps, so every component will see 2 amps. Therefore, IT, current total, is 2 amps. Resistance in a series circuit is equal to the total ohmic value of all of the resistors combined. When looking at figure 5.2, you have to add 30 ohms plus 50 ohms plus 20 ohms to get the total resistance of the circuit, which is 100 ohms. Power in a series circuit is equal to current total times power total. So looking at figure 5.2, if voltage total equals to current total times 2 times resistance total, which is 100, then power in a series circuit is IT times ET, which is current total times voltage total. So looking at figure 5.2, if ET equals IT, which is 2, times RT, which is 100, then ET equals 200. IT equals 2, then PT equals 400 watts. There are other formulas to find power in a series circuit. Refer to the circle diagram of formulas from lesson 4. Use the formula for the known values. Sometimes you'll have to solve other values to get a known value. When you want to solve for unknown voltage value, just use the same for the formula, but use the current and resistance across that particular resistor. Example: in figure 5.2, ER1 equals to ER2, which is 2A, times R1, which is 20 ohms. So ER1 equals 40. In figuring out the missing values of the previous circuit, in figure 5.2, we used Ohm's law and we applied it to ER1. Remember Ohm's law, figure 5.3 merely shows us the relationship of voltage, current, and resistance. If you know two of the three values, you can solve for the other. Please take additional time to understand this formula by changing the values in figure 5.2 and solving for the unknown using Ohm's law. Ohm's triangle in figure 5.3. Troubleshooting a series circuit is best done with a voltage meter. One thing to remember is most series circuits faults will have an open in the circuit. When an open occurs in a circuit, you will read ET, total voltage, across the open. An open is a break in the path for current to flow. The best instrument to troubleshoot a series circuit is a voltmeter. When referring to figure 5.4, if you put your meter across the switch, it will read however many volts the battery produces because it is open. If you push the switch down, the voltage across will decrease. The voltage across it will decrease. With the switch pushed down, if you take your meter and put it on each of the light bulbs, it will tell you the voltage drop of that particular bulb. If that bulb was open, the voltage drop across that bulb would read the battery voltage. In this type of circuit, there is only one path of current to flow. In this type of circuit, there's only one path for current to flow. So no bulbs will light if you have an open in the circuit. See figure 5.4 again. A parallel circuit is a circuit that has more than one path for the current to flow. Figure 5.5. In this type of circuit, the current can continue to flow through the other if one of the resistors is removed. Voltage in a parallel circuit is equal to source voltage. This means if we were to apply 15 volts to the circuit in figure 5.5, both resistors would read 15 volts on a voltmeter. Current, on the other hand, is additive because you have multiple paths. A little hint to help you remember this is that voltage and current are exactly opposite in a parallel circuit than they are in a series circuit. Figure 5.5. The current in each line, figure 5.6, of the parallel circuit is called a branch circuit, a branch current. Therefore, R1 is one branch and R2 is the other branch. The total of the two branches is called the mainline current or total circuit current. Resistance in a parallel circuit can be found 4 different ways. We will discuss the first 3 ways because they are the most used methods in the industry. You can refer to your textbook for knowledge of the graph method. Try to use the method that is most comfortable to you. The 4 methods are product over the sum, reciprocal method, equation resistance method, and the graph method. We will use figure 5.6 for this discussion. The product over the sum method can be used when there are 2 resistors connected in parallel with different values. The formula is RT equals to R1 plus R2 divided by R1 plus R2. So if we change the values in figure 5.7 to R1 equals R4 and R2 equals 2. Then RT equals 3 times 6 divided by 3 plus 6, which is RT equals to 18 over 9, or 18 divided 9, which is RT equals to 2. The next method we will discuss is the reciprocal method. This method can be used when there are 3 or more resistors connected in parallel, figure 5.7. The formula for this method is 1 divided by RT equals to 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3. If we plug in the values from figure 5.7 into the equation, it will read 1 divided by RT equals to 1 over or divided by 100 plus 1 divided by 100 plus 1 divided by 100, which is equal to 1 divided by RT equals to 0.01 plus 0.01 plus 0.01, which is equal to RT is equal to 1 divided by 0.03, which is RT equals to 33 ohms. The final method is the equal resistance method. This method can be used when a circuit has 2 or more resistors of the same value, figure 5.8. The formula for this method is RT equals to R divided N. R equals to the ohmic value of resistors, and N is the number of resistors. Looking at figure 5.8, we can plug in its value to this formula. RT equals to 10 divided 2, which is RT equals to 5. Power in a parallel circuit is the total of each branch circuit power added together. The formula to find power in each branch is P total 1 equals to E R1 times I R1. Referring to figure 5.9, we can plug in the values. PT1 equals to 50 volts times 5A equals to 250 watts. Now if you do this for each branch and add them together, you will get the power total for the circuit. If you were to remove any one of these known values, like figure 5.9, you could use Ohm's law to solve for the unknown value. I keep bringing up Ohm's law because it is the main key to solving most electronic equations. It is the beginning of your career. You should know it like the back of your hand. Troubleshooting in this type of circuit, figure 5.9, is best done with power off. It is a resistance check, or what most electronic specialists call a cold check. You are simply checking to see if any of the resistors are open. You can also do a current check on each line because an open resistor will show no current. A voltage check will not help you in this case because each line is already reading source voltage. A combination or series parallel circuit, figure 5.10, is a circuit that will have both a series branch and a parallel branch. You will have to use the rules for series and parallel circuits in this type of circuit. Looking at figure 5-10, the best way to approach it is to find your total circuit resistance first. You can accomplish this by turning the parallel circuits into series. R1 equals 50 ohms and R2 equals 250 ohms. You can use the product over the sum method to convert that part of the circuit, which is R1 and 2 equals to R1 times R2 divided by R1 plus R2, which is R1 and R2 equals to 100 times 250 divided by 100 plus 250, which is R1 and R2 equals to 71 ohms. Now you must do the same for the other parallel circuit. R3 and R4 equals to R3 times R4 divided by R3 plus R4. So R3 and R4 is equal to 350 times 200 divided by 350 times 200, which is equal to R3 and R4 equal to 127 ohms, 127 ohms. Now add those two together to get the total circuit resistance. 71 plus 127 equals to 198 ohms. The total voltage is already given, so use the Ohm's law formula to find the total current. Ohm's law formula is, in this case, is I equals E over R, or E divided R, which is I equals 24 volts divided by 188 ohms, which is equal to I equals to 121 amps, or 121 milliamps. Let's take it a step further to find the voltage and current drop across each individual resistor and leg. This is where you have to pay close attention and use your rules for voltage and current in both a series and parallel circuit. We have all the circuit totals. I equals 0.121A, E or voltage equals 24 volts, and R or resistance equals 198 ohms. We broke the circuit down to two series circuits, R1 and 2 and R3 and 4. We should find the current first because of the rule. We know current will be the same in a series circuit. 0.121A in 0.121 amps in R1 and 2 and 0.121 amps in R3 and 4. With the resistance and the current, we can now find the voltage across ER1 and 2 and ER3 and 4. ER1 and 2 equals to I1 and 2 times R1 and 2. The first leg will be ER1 and 2 equals 0.121 amps times 71 ohms, which equals to 8.6 volts. The second leg will be ER3 and 4 equals to IR3 and 4 times R3 and 4. So ER3 and 4 equals to 0.121 times 198 ohms, which equals to 15.4 volts. Now you can break legs up to find the current drops across each resistor, because you know voltage is the same in parallel circuits. Resistor 1 and 2 will see 8.6 volts, and resistor 3 and 4 will see 15.4 volts. By using the Ohm's law formula for current, you can find current drops for each individual resistor. IR1 equals to E R1 divided by R1, and so on with R2, R3, and R4. The numbers may be a little different, but it depends on where you round off. In this figure, I rounded off in 3 places past the decimal point. The answers are ER1 equals 8.6, ER2 equals 8.6, ER3 equals 15.4, ER4 equals 15.4, R1, resistance 1, equals 100 ohms, R2 equals 250, R3 equals 350, R4 equals 200. E, ohms, total, equals 24 volts. Current total equals 0.121 amps, and resistance total equals 198 ohms. Current current R1 or IR1 equals 0.0860, IR2 equals 0.0344, IR3 equals 0.044, IR4 equals 0.077. If you want to find power of each resistor or total power in the previous equation with all of the total values, current, voltage, and resistance known, set up the formula for power, which is P equals E times I, or P equals I squared times R. You must use the values for each resistor if you want to know the power for each resistor, just like you did for current and voltage. Troubleshooting this type of circuit combination can be accomplished with either cold checks, resistance, or with live checks, voltage or current, depending on whether you are trying to isolate the circuit or the components. Figure 5.11. And this is the end of Chapter 5 review. Thank you.